number 6, medical applications of pass recognition. Then we have Angel Hoyos for the first slide, and CICESE.
Good morning. My talk is Calamar layer to improve semantic segmentation in medical image. Well, semantic segmentation is a very well-known problem in visual computing, where we try to classify each pixel in an image. You can see in these examples. And some applications in medical image are to detect some organ, some anomaly, some tumor, or there are other applications like autonomous vehicles where it's necessary to classify in a very fixed level to a car, the road, people, and general purpose application. Okay. For the problem of semantic segmentation, is a very well known and actually the state of the art, the unit architecture. Okay, but there is also so many variants of this architecture, like ResUnet and the BGG UNet, where the encoder part is replaced by a architecture like ResNet or BGG. Okay, there are also another application like UNet 2 and 3, where there are more connection between the encoder and decoder part. Okay. An alternative to solve this problem of semantic segmentation, there is a conditional generated adversarial network, better known like pix-to-pix, and this kind of networks comprehend like a generator and discriminator, and are designed to generate image more than segmentate, but successfully generate discrete segmentation labels, like in this parallel. The main purpose of pix-to-pix is from kind of label image to generate, but also from the RPG image we can get the labels. Right? So, and the generator part of the pix-to-pix is the unit that we just said that is a very well network for the semantic segmentation problem. Well, this part, it seems like everything is fine, but we have a problem with segmentation classic labels. We have the one-hot codification. When we have one and where the class corresponds to some class label and 0 in other parts of the vector, right? But to change from one class to another is enough to change a couple of bits, okay? And this error can be in the training, in inference, or by adversarial attacks, or it can be in any moment. So this problem also happens, or is more common in the information transmission information, when we have a message that we encode and we pass to another server, in this case, but there is some noise that change these couple of bits that we just commented, and change the original message. So in this case, change the message, and our problem is semantic segmentation, change the class. Okay? So one solution for this problem is the linear error correction codes, like Calamar codes, and these codes add redundancy to the message to be to secure the message. If there is some random flip bits from some noise, the message is still the same. Okay, so we use the Calamar codes with two reasons mainly, because it's easy construction, so recursive reconstruction like we have here, and at this time some examples of the Calamar matrix with size 2 and 4. And we can see that this H2 matrix is right here, right here, right here, and the negative like is in this definition, right? So we change our labels to one hot labels with a new row from this Hadamard matrix from product. Another nice property is that the product for the Hadamard matrix and its transpose, we get an identity matrix of size n, b, and the size of the Hadamard matrix. And this we can have our identity matrix again, right? So this problem we used previously in adversarial attacks classification with subset, where we change the codification of the labels, and even if there are some errors or random flips in the code, we have the correct classification. Okay, so to resume what we talked about at this point, is we have a medical image and its segmentation. We are going to use a pix-to-pix and with the Hadamard code for the labels. Okay, and where is the Hadamard layer here? Well, the Hadamard layers in the pix-to-pix architecture is going to be right here at the output. As we say, we change the labels for each class for a Hadamard code. So the output of the generator is going to be a Hadamard code, okay? And the Hadamard layer is going to do the product multiplication between the transpose of the Hadamard codes and the prediction of the codes. So to get the identity matrix, and that's we are going to pass to the discriminator and the load function, and we are going to have to change every part of the network. Okay, and actually another advantage of just this discriminator is that we have some patches in classical GANs. We only have fake and real, and the discriminator we have some patches that we have see one part of the image is a good segmentation or not, better than the whole image, right? So we evaluate this Hadamard layer and two datasets, and medical segmentation declaton and the task of log, and liver tumor segmentation benchmark, right? And this is the image and the training image, and this image we train this. Okay. We investigate the performance using the Hadamard layer with a traditional codification, the one hot, and in pix-to-pix architecture with the UNED, BGG UNED, Res UNED, and UNED 3 Plus models. Okay. The metrics for this work, we use pixel accuracy, which we count the number of correct classified pixels over the total number of pixels, and intersection over union. We can see an example of it. This metric penalizes if a pixel is in the wrong place classified. Okay. We can see here the table for the long and the medical segmentation decathlon, and we can see a better performance in each model that we tried. Okay, and in the image, I think in this part, maybe. Okay, the next image is better. But if you don't see anything, it's because the model didn't get anything from the traditional training. And right here is a little red part, and this part is almost the same, but this is the state of the art unit for this type. Okay, this is not very well, but this is like a binary group that we have, like organ and background only. Okay, and we have the liver tumor dataset, the segmentation, as in the previous dataset. We have a better results with the Hadamard layer. Okay, and this, yes. this is better. Right? Okay, and we can see the target and the segmentation for each model and each codification. Okay, and the one hot with the unit true plot, we can see that the tumor is bigger than the target. So this is for a medical auxiliary, but it's very bad, no? Because we have to say to the patient that you have a very large tumor, with the real one is smaller. So even if the unit true plots don't recover the exactly the same of the target, is a better approximation than the one-hot codification. And in these examples from here is almost the same. We can get a better representation, like this part is kind of red, is all green on this part. Okay. We also try our method for face segmentation, even if it is not directly medical image, but is an auxiliary for plastic surgery. So as the previous work, is a more larger number of classes. So on this work, it's also almost in every case, with the Halmar layer is better than the one-hot. And here are some examples that we can see that it's a better segmentation for each part and each one in the model. Of course, some classes like glasses or is very difficult, but there is no many examples of that class, so it's hard to get a better segmentation. And well, as a conclusion, we propose to use a Halmar layer, the simple computational and efficient way to improve the results in medical semantic segmentation tasks. Okay, the results of the Halmar layer substantially improve the performance and the metrics that we showed. And okay, and why this happened? One explanation is that using this change of codification, we force to the network to be all the bits at the last layer more active. A difference that the one-hot codification will only have one bit. Okay, as a future work, we are currently working with a more challenging segmentation task, and that's this one, and we are pretend to work with 3D image as well using this. And that's it for any question?
Thank you Angelo for the presentation, and is there any question?
Thanks. In the competition that you talked about, how did you measure the performance? Each image is an array of n by n. So you check the portion of good assignment, or is any special performance?
Yes. Well, different. One difference in the typical evaluation is that in segmentation you have every layer for every class. Okay. So with the Halmar code, you have a larger part of the channel. But you do a array max, so to get the end-for-end image. And in that case, you use a typical pixel accuracy and detection over union evaluation. So we don't have to change the evaluation. And just in the training for the generator, we evaluate that with the m-square error, that the output be a Halmar code like we defined at first. But this part of the load function.
Another question? I have one related to the robustness of the method. Did you try or test change the scale of the images, the size. I mean, reducing the size of the images.
Yeah, we tried like in the long dash because it's like a very small part. We try to scale and rotate and augmentation part. Yeah, we tried that and it's not because it's at pixel level. So let's to have only a pixel for the pixel, so it's not.
Okay, thank you. And here we have, thank you very much. Here we have your certificate of participation. And we have the second talk by Moisés León. Yes, Alvarado, please.
Thank you very much.
Well, good morning everybody. I'm going to explain this my paper that is named Patterns in History of Breast Cancer Tumor. I'm from CICESE, IPN, and well, this is going to be the content of the presentation. And well, cancer is a very public challenge in all the world. Only in Mexico reports more than 1 million deaths associated to cancer. From this, 100 of cancer deaths is associated to malignant tumors, and of this, 8% is from breast cancer. Also, the World Organization of Health, WHO, recognized that breast cancer is the most common in the world. It reports more than 2 million of cases in the same year. Well, we have identified some features or phenomena that are common in different kind of cancers. There was the hallmark of cancer that were presented by Hanahan in 2000 last decades, and there are updating subsequent works in relation to the cancer. Some of the indications that promote the cancer formation have been detected, and we can relation to mutation in some genes. Also, in this research, we are going to identify the principal genes in the formation of the cancer by using gene profile expression from biopsies of cancer. Well, the popular practice to identify the cancer is very expensive in money and in time because there are very heterogeneous problems, and there are no two cancers that are equal. But in the fact, the genes that get muted or the proteins that promote the cancer are the same in the most of the cancer. So we also the experiments in silico may give us more tools to identify this problem, to get simulations to analyze information that not are only from image. For example, in this case, as I said, we are using profiles of genetic biopsies, and we identify genes. Also, in silico is cheaper and is faster, and we don't need a lot of resource of computation. The methodology that we use is the next one. First, we download the databases. We create a dictionary and normalize this data set. We introduce URAGNet, that is the algorithm that we use. We get we prune the output from URAGNet to make more handling the the co-expression matrix, we generate analyze the genetic networks. If we use some pre-hooks to run this co-expression matrix, and if we see that if we have a good threshold, we do some simulation, and if not, we modify the threshold and repeat the process. And finally, we get the average of the results. Well, we obtain the data set from two repositories. One is GEO, that is the gene expression omnibus, and GDC DP, that before was the TCTA, that is the Genome Cancer Atlas. To the treatment of and normalization of these data sets, we collect the raw data. This is very important because the data sets contains a lot of information that are not useful for us, because it contains the age of the person, the sex, the race, and more information that is not relevant for this information. We only get the profile expression and the transcript per millions of each gene in the samples. So we normalize the data, we apply to reduce the domain of the data, we apply the logarithm to normalize the data. After that, we validate the information and import data to the databases. We use information sharing algorithms that basically use the entropy. The entropy is shown in the first equation, that is the entropy of Shannon of sector information. And also with this entropy, we use the mutual information that are going to say us how much is interaction a pair of genes inside the co-expression matrix. Also, we use the probability joint distribution probability, to see which are those interactions more important in the genetic network. From ARACNE, as I said, it was the algorithm for the reconstruction and accurate cellular networks. This is, we use the multi-core version because it's faster. There are also some other algorithms that use the information theory, but this, we think that this is a consolidated algorithm and it's very efficient. From the samples, we obtain 130 samples from primary tumor, 90 from first metastasis, and this is, as I said, because there are from different databases, there are different number of genes. So when we apply the normalization and of the databases, we get 40,996 genes, and in two different files. RNA, which give us is the main interaction between the pair of genes. Well, as I said also, we run the expression matrix that ARACNE give us to make it more handy. If we want to use the original output from ARACNE, we obtain files from gigabytes. And if we use different thresholds, we obtain files more handy, and we can also graphic these genetic networks to identify the centralities and the topology of the genetic networks. Well, this is an example of a genetic network that we make. We can see that this is a local connect genetic network, and we have an average of the degree of 104 interaction. This degree is the number of connections, or the average of the number of connections that each gene had with other genes. Also, we analyze the distribution of the genetic network, and we look at this power law distribution. This also can give us information, because the prune, we get some genes that have no high interaction, they are not affect the topology of the genetic network. Well, in this table we can see which are the genes with more mutual information, and that's the genes that have well, these genes later we will analyze and compare with information with bioinformatics software to identify which are the biological process and molecular functions. Also, we make to make more robust this analysis, we make a statistical analysis with the 100 simulation of the same tissues, and we get the same process. We input the data to our net, we run the previous matrix, we build, analyze the genetic networks, and the individual results we collect and get the average of this. And the average change with the results of a single topology, of a single genetic network. These are the genes that we obtain. This is the degree, the total degree of the 100 simulation, and this is the average of this degree. As we can see, some of the genes that have more mutual information also have a lot of number of connections in the genetic network. So we to continue with this analysis, we take tissues from primary tumor and tissue from first metastasis in breast cancer, and we identify the main genes that have in each tissue and compare it. Well, for the space, we only analyze here the first 5, but we can analyze all the genetic network, and we identify some genes that are present in the two genetic networks. And cells, for example, some of these genes are associated to translocation molecular functions, and this is, well, in the analysis of the biological, we can say that when a tumor of cancer wants to get the primary tumor and locate in another organ, it needs to, these genes are more expression to get the metastasis. So the results that we are getting are good. Well, these are some of the genes more important. Also, we introduce this conjunct of genes to gene ontology. Gene ontology is also a bioinformatic software that says the functional, the biological function of some of these genes. Well, from the discussion, we identify the main genes of breast cancer and primary tumor by the genetic networks. Statistical analysis. This analysis extends the methodology previously applied on the single first breast cancer that we have in a previous paper. Genes with the highest mutual information and the highest degree nodes are most of the same respectively. So this, as I said, gave us information that we are doing good the process. As a conclusion, well, we after the 100 simulation, we identify the main genes of the breast cancer. For each lead node, we have mutual information that it could be indicate the relevance of the formation of cancer. Well, the genetic network gives us a power law degree distribution, and this also give cells that are real networks or networks from the real life. And well, there is a small interaction with the set of main genes of the genetic networks of primary breast cancer and metastasis. And from future works, we are going to add another tissue that it will be non-cancer tissue to identify which are the genes that are expression and make the formation of cancer from a tissue that has no cancer to the metastasis. And that's it.
Thank you, Moises, for the presentation. Is there any question?
I know that it's very difficult to have people in these stages of cancer, but what is the impact of the, let's say, the sample size? In this example you show, if I remember well, 130 in the initial stage. Your conclusions will change if instead of 130 there were thousands or more?
Thank you. Yes, well, when we start this research, there are not a lot of data sets, free data sets, because are information, but are, because it's health information, there are no free, or there are no open access. But if we want to improve in this research, we can pay for the data sets to get more information, or, well, there are varying some data sets, and we can improve to get more information, more data from this. And well, this is because we have breast cancer, but also we can make with any kind of cancer, we identify which are the main things.
Thank you. Another question. I have one related to that. How relevant is your work comparable with other works?
Well, there are no literature about this, so we think that we are improving in this area. So we don't find some literature with this. So yes.
Thank you. Another question? If not, thank you very much. Moises, you have your certificate of participation. Thank you very much. Then we have the third talk by Lacey Torres Rodriguez and collaborators. Please.
Good morning. My name is CICESE Rodriguez. I'm working Informatics Research Center at University Central Artabrego de las Villas, Santa Clara, Cuba. The topic of my research is realistic simulation of event-related potential and the usual noise and interference for pattern recognition. Well, the signal obtained from simulation can be used to train, evaluate, or compare different digital signal processing techniques or pattern recognition algorithms, giving research the possibility of limited number of the signal for experimentation. Monitoring brain activity from electroencephalographic recording is very popular, but evaluating the method of analyzing the signal is difficult task because there is generally no gold standard that allows comparison. However, evaluate different algorithms proposed for the analysis and detect pattern from the signals. Research often uses simulated signals instead of real signals, which usually fit to simplicity model far from reality. What is the objective? Well, the aim of this research is to obtain simulation of event-related potential recording with a high degree of realism. For the simulation, the possible variation that might appear in the latency of the potential, in the wide variation of the main component that forms the potential, and its amplitude are taken into account, are considered. The event relay potential in real context can be contaminated with additive and multiplicative noise, and also be affected by the effect of the instrumentation we're recording. The analog filter state, sampling, or quantization. Small scoring evaluation in these aspects are ignored. What is the scheme for the simulation? This is a scheme for the simulation. The block 1 is the block responsible to obtain different variation to original waveform. What is the variation? Well, the variation is displacement and different possibility of the delay of the signal, and other variation is introduced dilation and contraction, was are characteristics of the signals. The second block is to complete the register, the record. At this introduction, each segment for completion the signal. The third block is a block for addition noise, additive noise, and addition multiplicative noise. In the fourth block, we consider the different characteristics related with filtering, sampling, and quantization. Well, what is the selection of the parameter for simulation? Well, the first parameter is X0. X0 is basic waveform and is used as a reference to generate n-1 equals more. The initial waveform resembles as much as possible the waveform of the potential that you want to study. In this particular case, the clean recording of auditory evoked potential in healthy subjects, providing the database published and described in Physionet. These signals corresponding to auditory brain response, APR, the short latency potential. And those, some authors suggest that this early response is characterized by having a low variability in its latency and amplitude between subject and within subject. But numerous papers try to solve the sensitivity of the average techniques in the presence of no alignment that can appear in the signals, show that the evoked response do not always appear perfectly aligned. The second term, tau I, corresponding to the variation to relative displacement due to the latency that can be present in X0, is simulated following a low normal variation with zero mean and standard deviation of the order of 0.2 milliseconds. This value was chosen from the mean value of the standard deviation of the component 5 latencies according to the different studies. Alpha I, corresponding to the variation of the width of X0, is simulated following a low normal variation with zero mean and standard deviation of the order of 0.07 milliseconds according to different studies too. M is the number of evokes for the simulation. Other parameter is T. T refers to event period. Is select according to the stimulation period, which in this case was 2002 samples. 2002 samples for frequency sample of 40 48 kilohertz is 41.7 milliseconds, corresponding to the time elapsed between each applied stimulus. A is the wide of analysis window. In the case was 884 samples. This parameter can also be modified according to initial basic epoch chosen and the potential to be simulated. Can be changed. Well, NT. For the addition of the additive node is a problem, which in the case is a sum of the estimation of the background noise plus the 60 Hz interference and its harmonics plus the alpha hit that is presented many of the signal of the database, and analysis of the raw record providing the same database was performed. In this case, record where a user where intensity of the stimulus was equal to or less than 30 dB SPR, sounds per soul level. The justification for this selection is based on the fact that in this recording there should be no auditory response. Therefore, they should only be constituted by the basal activity, the G signal, only the G signal. For the simulation of the alpha hit that is presented some signals, and they can be taken consideration when analyzed to homogeneity of the signal, which can affect the result of the average signal that is estimated. A white noise that is filtered with a bandpass filter with Butterworth approximation of order 2 with a cutoff frequency between 9 and 11 Hz. As applied in different publications, that amplitude for this reading was between 30 microvolt and 50 microvolt, randomly distributed, with a normal distribution, and it is in total agreement with the analysis carried of the data set. The features show, for example, component associated to alpha hit presented in the signal studies. The parameters related to filtering, sampling, and quantization are taken from the description that is made on the acquisition of the database. For the simulation of a ground noise, the analysis of the raw record was done. The following section describes the analysis of the raw record for selection for the model for the simulation of background noise. Well, for selection of the background noise simulation, the best model, autoregressive models have been widely used in the representation of EEG signal because they allow a compact representation of various types of rhythms of the EEG signal. The fit of the parametric autoregressive model to an EEG signal involved the selection of one sending parameter, the order of the model. The choice of very high order can cause overfitting of the model and introduce incorrect information such as false peak in the spectrum. A very low model order can lead to loss information, which in the frequency domain is seen as smooth. It's a smooth spectrum. The most appropriate order for the model is the one that minimizes the information criterion, where is evaluate over a range of giving order. For the simulation of a ground noise, different methods of DIR model were compared. For noise modeling, we compare to regressive model, but based on the covariance, the modified covariance, the Wood model method, the Euler-Walker method, and the linear prediction component using Bayesian information filter. This feature show the Bayesian information criterion obtained using different methods. The covariance method, the modified covariance base, and the Wood method present the best result and do not differ between them. We will decide to choose the Wood model because guarantee that this estimate parameter corresponds to a stable AR model. Aspect must be taken into account, which is required to simulate signal or use the model parameter for the classification of EEG signals without the need for additional calculation. A good compromise is to choose works methods with order 5. There are no major changes in the information criteria. Several applications in the bibliography using order between 5 and 8. Higher order is only justified when much more detailed power spectrum specifications are required. The other interference, the 60 Hz interference and its harmonic, were removed for the signal using a comb filter to make the model adequately fit the background signal. From the spectral analysis for the original signal before applying the comb filter, the peak of the frequency response, the amplitude and phase were estimated to generate representative 60 Hz interferences and its harmonic for the simulation. For this, an array was created to include this data, which are selectable when simulating. The evaluating model provides an adequate estimation of the signal for the highest frequency. In this part. But not for the lowest frequency, where the characteristics of the high-pass filter are not detailed. This could also be caused by the high sampling rate and the very low cutoff frequency at low frequency relative to the cutoff frequency at the high frequency. For resolve this problem, on filter with Butterworth approximation was designed. The characteristics of the Butterworth high-pass filter it shows in the table 1. After specifying a model and estimate its parameter, it is necessary to check the goodness of fit of the model to the original signal. For this, different cost function can be used. In this case, the cost function, the normalized root mean square error, is used to stabilize the comparison. Values close to 1 indicate a good fit for the model. The table 2 shows the values obtained for all the items saved and studied. For a total of 102 reports analyzed, the values of the coefficient estimated by the AR model can be seen in the figure 3. Although there is some dispersion in the values of the estimated coefficient, they do not differ significantly from each other for the total number of records analyzed. To obtain the similar noise signals, Gaussian white noise was generated, which was low pass filter with the coefficient estimated by the model. The coefficient is shows in the random form. Then the noise was a pass filter using the filter with the specification in the table 1, and later it was the 60 Hz power line interference. At the analysis was performed in 1 second segment of the signal to guarantee the stationary condition. The following features show the comparison, the spectrum of the simulated background noise, and the reference signal. The reference signal is the blue line, and the simulate is the red line. The second feature is the comparison in the time domain. A frequency domain comparison of the simulated signal with the specification described above is showing the following features. In all cases, the normalized to mean square value remain higher than 85%. The following picture we can see the variation in this display, the variation of the relative displacement change in the amplitude and change in the width of the may be present in real scenario. An example of simulation including noise, interference, and artifacts we can see in the following features. For this example, signal to noise rate obtained is minus 26.32 decibel, is order along the realistic scenario. Yeah. Future work is the construction of tools that allow the simulated signal and compare different digital signal processing techniques or pattern recognition algorithms for estimate the embedded signals. Conclusion: simulate how recording of potential allows obtaining a controlled data set for evaluation of new methods for evoked responsive detection, and 8 order AR model using board method provide a good estimate for the background noise, interference in real signals, such as the 60 Hz power line interference, the alpha ring, and instrumentation channel noise can be simulated. The scheme has allowed the addition the out of range values on impulsive noise. Any question?
Basic for the presentation. Is there any question?
Thank you. I just have one question. Is the model per patient or is general? I didn't catch that detail. Thank you. Es por pacientes.
For the question.
Yes, the coefficient was estimated for patient. I obtained a graph where with all coefficient in the process, the simulation, I chose a random for the simulation.
Okay. Okay.
Another question? If not, thank you very much. We have for you the certificate of participation. Thank you very much. Now the next talk we have online or video. It's online there, no? Or video? Online. Okay, the author is not connected, then we will watch the video of the presentation.
Good morning. My name is Eduardo Garea. I am a researcher at the Cuban Neuroscience Center, and I will present the work entitled CICESE Imaging Severity Score of COVID-19 Pneumonia. This is a work by a group of output from the Center of Neuroscience in Cuba in collaboration with the Free University of Belgium. As introduced in this work, we can see that after 3 years of the fight against COVID-19 pandemic, the protocols and forms of action in treating patients in severe or critical conditions have been constantly renewed to arrive at the first stand to save the patient. Checks X-ray images were frequently used in diagnosing the disease, and many medical research facilities in developing countries such as Cuba. Several studies show that imaging patterns in CRA images that are characteristic of COVID-19 may decrease or increase depending on the state of severity of the patient and the effectiveness of the protocols applied. On the other hand, deep learning techniques have been widely adopted for COVID-19 classification of CICESE. The main advantage of deep learning method from CICESE image classification is the capability to capture pixel level information which human eyes cannot obviously notice. In the study carried out for this work, we have been able to see the use of CNN network as unique 6net DenseNet VGG9 OVNet in section 3 ResNet 18 ResNet 101 and SqueezeNet for tasks such as COVID-19 nuclear screening, COVID-19 diagnosis, RX classification in COVID or non-COVID, evaluation at different scales, global or local, of the degree of molecular affectation caused by the disease. On the other hand, CICESE severity scoring systems have been proposed to map a global region-based quantitative judgment, assessing the distribution of pulmonary involvement of COVID-19 on a quantitative scale. For example, in the radiographic assessment of pulmonary edema rate, the thorax is divided into 8 quadrants. Each quadrant was assigned the product of a consolidation score and a density score. The rate score has been adopted by Cuban Society of Imaging and used to develop machine learning approach. Based on rate scoring, this paper proposed an end-to-end severity assessment method built on recent proposed semantic genesis-based classification. In this slide, we present the general scheme of the proposed method that consists of two main steps. First, quality evaluation, enhancement, and loop segmentation. And second, image semantic classification and severity level evaluation. After evaluating the quality of the image, the algorithm established a conditional state that allows the quality of the image. For this, an adaptive histogram equalization is adopted. The segmentation of the loop is done using a trained CNN model. After a long region segmentation and a normalized image rotated in scale, standardized size of 180 to 180 pixels is obtained. On the normalized image, we perform image cropping into 8 pages, corresponding to 8 quadrants of the rate position. Once the patches corresponding to each rate quadrant have been extracted, the binary classification between affected or non-affected is performed based on semantic genesis approach. For this, the training of the unit to use the model was developed. The obtained patches were previously labeled according to the presence of non-affectation. These slides show the training scheme of the proposed classifier. Following the semantic genesis approach, this process is divided into two parts. Anatomical pattern classification. The classification branch encodes the input anatomical pattern in the latent space, followed by the sequence of fully connected lines, and predicts the level associated with the pattern. Previously, a series of transformations were made to the input image that allow obtaining greater robustness in the extracted near future field, serving as a data augmentation method. In our case, we assume the series of transformations proposed in the original semantic genesis paper that are linear, nonlinear, local shooting, out painting, and in-painting transformations. The second step is restoration of anatomical pattern. The objective is for the model to learn different visual representations by discovering original anatomical pattern from the transformed one. The restoration branch encodes the input transformed anatomical pattern in the latent space and decodes it into the original resolution to recover the original anatomical pattern from the transformation. For training the model, we define these loss functions for the multitasking restoration and classification, where gamma CL and gamma RC regulate the weight of classification and reconstruction loss, respectively. LCL is the loss function of the classification process by a binary cross-entropy loss function. LRC is the distance L2 between the original pattern and the reconstructed pattern expressed as eros function. Once the classification process has been carried out, the degree of severity of classification is estimated. For this, the same described in Gray methodology is followed. If the patch is classified as affected, it is assigned the value of 1. Otherwise, it is 0. The final score is obtained by summing the values assigned to each part. A severity score is assigned to the image according to the values of this table. Training and validation of the proposal take advantage of multiple datasets of CICESE images from Q1 hospitals. The images were taken from May 2020 to December of 2021, including 500 images of patient diagnosis with COVID-19 and 154 images of healthy people. From them, a group of 365 images was selected. 50 of healthy people and 285 of COVID-19 patients that had been fully documented and evaluated by the radiologists of this hospital. From them, 2,680 level training samples were extracted. This data set was divided into three sets. Training set with 2,144 samples, validation set with 268 samples, and the set with also with 268 samples. The dataset was labeled according to the two classes corresponding to the affected quadrant and unaffected quadrant. For the implementation of the proposed model, the transformation from 3D to 2D of the unique 3D model was performed. The original model was taken from the open source implementation of the official site of semantic genesis approach. The implementation was carried on the open source library CICESE with MIT business writing in Python. All training sessions were carried out on PC with Intel Core i7 471 H2 processor and 2.30 GHz and 16 GB of RAM. During the training process, we have balanced the training data by randomly sampling each epoch the same number of pages for each class from all possible pages for that class. In the training procedure, the input image and their corresponding labels were used to train the proposed model with stochastic gradient descent. We applied the document estimation Alan method. The training process was carried out for 100 epochs. To compare the performance of the proposed model, we tried three backbone models from classification, namely BGG 16, ResNet 15, and MCPR. For the evaluation of the performance of the proposed model, the accuracy measure was used. The results of time are shown in this table. Two accuracy values were measured. The first accuracy obtained in the training process, and the second test accuracy on the test set using the training model. It can be seen that the proposed model and ResNet 15 obtained the best result with a similar performance in the test set. To verify the robustness of the results obtained by the integrated classifier, we developed a process of evaluating in a tenfold cross-validation scheme. In order to compare the performance of the proposed model, this same cross-validation scheme was applied to the ResNet 15 model, which achieved results similar to ours in the first experiment. For our experiment, our dataset was of 2,680 samples, was divided in tenfold of 268 samples each. And the model was tried and tested using the tenfold scheme. The slide shows the obtained result. It can be observed that also the average of the performance measurement of the proposed classifier is 0.968. The classifier maintains its accuracy in all folds above 0.95. However, the ResNet 15 model did not maintain the same performance in the tenfold, obtaining a final average of 0.875. To evaluate the effectiveness of the proposed method, we compared the performance of our proposal with the proposal of Garea et al. 2021 and 2022. To do this, we selected 75 CICESE images, 20 of which correspond to the healthy people, and 55 COVID-19 patients with different degrees of involvement. This set of images was not previously used in the training and testing of the classifier. The set of images was processed according to the rate classification by a group of radiologists specializing in thorax from the Cuban Society of Imaging, obtaining samples from level 1 as ground truth. For this, the sensitivity and specificity metrics were calculated. Table in this slide presents the result of these metrics obtained for the evaluated method. Figure in this slide shows the confusion matrix of both methods. The result obtained demonstrate the superiority of the proposed method by obtaining better values for sensitivity and specificity in the preliminary classification process of the rate one. Therefore, this improvement will have an impact on a more reliable evaluation of the degree of severity of affectation. As conclusion of this work, we can see that we present an algorithm that evaluates the degree of severity of the affectation caused by COVID-19 in the pulmonary region of CICESE. The results achieved in the experiment on images of healthy patients and those affected by COVID-19 show a high sensitivity and specificity values compared with the state of the art. Thank you for your attention.
Well, then the next talk is about this titled website creation with model fluid evolutional network and a new data set of fluid semi-complete samples by Juan Ramírez Quintana and collaborators. Well, hi, thank you all for coming. My name is Armando Reyes, and I came in representation of the Dr. Juan Alberto Ramirez Quintana for the paper Leukocyte Detection with Novel Fully Convolutional Network and a New Dataset of Blood Smear Complete Samples. We came from Chihuahua, from the Instituto Tecnológico de Chihuahua. Well, here we see the content during this presentation, we'll be seeing a little bit of an introduction, the description of the dataset, the proposed fully convolutional network, the results, and conclusion. Well, let's start. Well, first, leukocytes are cells that are part of the immune system cells. They can be divided into 5 types: lymphocytes, monocytes, neutrophils, basophils, and eosinophils. The 5 of them can be divided, just for your knowledge, into 2 groups: granulocytes and agranulocytes. Here we can see that granulocytes have like these little dots inside the cell, and the agranulocyte doesn't. So, well, the analysis of the cells, of the shapes, size, and number, and during a blood smear sample, is crucial for the diagnosis of diseases of people. So, we must consider that this analysis is difficult for clinicians and hematologists. Here we can see an example of a blood smear seen from the microscope. Well, because of its difficulty for the analyst Many researchers analyze images of leukocyte cells with different tools like color normalization, nuclei identification in cytoplasm, or tools like supervector machine and fully convolutional networks. For machine learning networks, they have been developed different types of datasets, public or private, with cropped images of leukocytes, and with different types of textures and color patterns. Here are some examples of the images shown in some databases that are leukocytes segmented manually. So, according to experts, it's essential to design algorithms to segment and also classify the leukocytes from the blood smear samples. Because as I said before, we can see various of textures, color variations that are not considered in the datasets from the literature. So here are 5 examples of datasets that you can find in the literature, like Ravi WBC, Rosa Lipo, blood cell images, blood cell detections dataset, and WBC images. Every one of these datasets represent normalization, the same kind of stain. So it doesn't vary the color of the cells. And that is something that may need to be considered during the classification and detection. So in this paper, we present a leukoset that is in a novel method for leukocyte detection named color normalization unit called QNet. Well, the leukoset is composed of 1,497 images of blood smear samples acquired with a microscope using a protocol developed in real clinical laboratory environment. And QNet is a fully convolutional network based on the units for leukocyte detection. Well, the datasets. There are a few datasets that can be available in the literature regarding the leukocytes. So most of them, as I said, focus on leukocyte classification with only cropped images. So this dataset shows now images directly from the microscope. We have a microscope where we put our sample, and then on top of it, it has a camera that is connected to a computer to take up the images directly from there. So we have 497 images, high resolution, with different kind of augmentations, 4x and 100x, and each one of them has its own ground truth. Its ground truth has marked the nuclei of every one of the leukocytes on them with a different color. The color indicates the class of leukocytes that it represents. Here we have the different classes that we have on the database, the 5 that I mentioned, and also a new one here, the 4. So all these images were used with a standard protocol of blood smear with venipuncture and collecting tubes with anti-hero. And we use the right stain method. Here, this database is public, and you can access it in this link of Drive on Google. Well, during this dataset, we use the same protocol and a stain, the right stain. But it needs to be said that in many laboratories, there exists many variations with the stain. Because of what? Well, the due date of the stain makes it to have a variation in the color of the sample. So we use the stain mainly to distinguish between red cells and white cells or leukocytes. So the stain, even if it has a due date, it still works. So, an analyst can see the sample and still recognize each one of the cells. But it takes a variation in the color, really. And for a deep learning model, that needs to be considered. So here we can see the architecture of the proposed unit. There is a variation of the model unit. We have an input, of an RGB image. Then we have a stage of color normalization, an encoder, a bottleneck, then a decoder. Well, starting from the color normalization, as I said, it's, the inputs represent different variation of the color. So, first, the color normalization makes them all same kind of equal. Here you can see this one is a little green, then it's like whitish, and this one's too. So, the architecture has three colors. The first one learns the features that separate background artifacts from the raw cells. The second one learns features that separate erythrocytes from the leukocytes. And the third one learns features that inhibit erythrocytes and receptor leukocytes. Then, as I said before, we have the bottleneck, and that separates the leukocytes from the rest of the objects. Then the decoder to get the output at the same size as the inputs. And last, we have an output that tries to binarize the image. So the base model is an output image of RGB color. So now we add here binarization to just get an output from like segmentation. Well, we trained this in a Ryzen 5 processor with a 63 gigs of RAM and an NVIDIA RTX 2060 Super. With an Atom optimizer, a learning rate of 0.0001, a loss function on cross entropy, and 6 epochs. We compare this network unit with a ResNet 50v2, ResNet 34v2, and MobileNet v2 with the metrics of accuracy, time to train the network, and the inference time. Here we can see the comparison with those all those models. All of them were implemented in the same computer. And here we can see that the QNet has a better accuracy performance. Maybe not the best timing for training, the second one, but considering the inference time, we have the best one compared to the other models. So in conclusions, we present two contributions. The first one is a new dataset named Leukoset of 1,497 images of complete looks smear samples for leukocyte segmentation and classification. And the other is the model unit for color normalization of units. And we have a better inference time and accuracy than other networks. And that will be all. Thank you.
Thank you. We have time for questions. Is there any question?
Is there any reason for the balance of the classes in your data set? And what is the impact of this balance or lack of it in the results?
Well, this dataset was provided from another university from Chihuahua, the Universidad Autónoma de Chihuahua. This is a collaborative project with them. And we try to take all of the samples that we can, all that they gave us. We take it, we process it, and then, as you said, we got an unbalanced dataset. So that does affect the training. And I really don't know how much in this work, because this is not my work, the next one is mine. But yes, it does affect the balance dataset.
Another question?
Thank you for the presentation. How much time do you need to get the architecture of the unit that you propose? How much time?
Okay, time for the architecture for implementing or for training?
Was it hard to get the architecture of the unit that you proposed?
No. It was, this work was performed with PyTorch, and they established all the layers manually. And well, they trained it from scratch, so it wasn't a problem like for the parameter setting and all that.
Another question? I have one. Previous table. It seems your method is the best for the masters.
Yes.
Yes. And that accuracy results is considering the testing or the validation.
The validation. Those results are for the validation set, and the accuracy is measured well from the output that it was minorized for segmentation. And yeah, well, we have the best accuracy and inference time compared to the other modes.
Thank you. Another question? If not, then we have you certificate of participation. Thank you very much.
Thank you.
Stay here because you are the same speaker for the last talk. Then the last one for this session is again is related to CICESE or recognition using a modified AlexNet and image to image GAN data augmentation.
Well, here is now my paper. It's called Logos and Recognition using a modified AlexNet and image-to-image GAN data augmentation. Well, here's the content. We will be seeing a little bit of an introduction, a dataset description, levels of classification model, the results, future work, and some references. Well, first of all, we're talking again about blood tests. Well, blood tests are considered the most common test to diagnose some people or patients with a disease. In the blood, as I said before, there are 3 different types of cells: leukocytes, blood cells, and platelets. Carrying out an analysis of the number of leukocytes that a person contains can lead us to know if that person has an infection. It can be also known as, we can detect certain type of cancer. So we're going to be focused in the white blood cells. There are 5 types of white blood cells: the basophils, eosinophils, lymphocytes, monocytes, and neutrophils. Here can we see some examples of our datasets. Well, a leukogram is a count of just the leukocytes from a blood smear sample. So when using a method such as a blood smear method, which is this one, you can see that in a slide we put a drop of blood and then we make a smear, and this slide is put in the microscope and analyzed by the analyst. So it can be lead to failures due to the blood smear process made by the person. If you don't make the smear good, it can be shown a bad sample. And also the count, the person can fail during the classification of the cells, and therefore it's a long process and it can lead to human error. So we sought to automate this process with deep learning. In previous approaches, the leukocyte classification in state-of-the-art works has been solved with some feature extraction models and a support vector machine for classification, or also with ensemble learning using different kinds of models and then ensemble them for the classification of leukocytes. So here we propose a new method using solving the task of leukocyte classification using only one classifier model and with a novel database that I was talking to you before. So, well, why taking just one classifier model? Well, in order to, in a future work, implement that model on an embedded system, and as we know, we have less computational resources in an embedded system. Let's talk about the dataset description. Well, the new dataset, as we see before, has the original image in the ground truth. Here's an example of the original image that was taken from directly from the microscope and its ground truth. Here we're seeing 2 leukocytes, both of them red, and that means that both of them are neutrophils. Well, then we got a detection stage in which we get the input directly from the microscope, and then we mark with red circles the leukocytes that were detected in this sample. For example, here are two of them. For this process, we use machine learning traditional methods for looking for sample size and encoder. Then we get to a crop stage in which we're gonna generate a new database of leukocytes that are segmented. This one will be used for training the classification model that we will see furthermore. And here are some examples of the already cropped images from the original image directly from the microscope. So this process is a little bit more like attached to what an analyst see, because the database that can be in the state of the art, they're already at this point, but they doesn't tell you how they did it. So this is a more accurate process, considering what an analyst see every day in an laboratory. Well, here we can see the distribution of the OGDB data set, that is segmented leukocytes, and we have a total of 558 cells. This is, well, a little samples for training a deep learning model. So we propose a method for data augmentation using a GAN model. Here is the methodology that we use. We are going to take the OGDB database and train a GAN model that is a transformation from image to image to generate artificial samples to have more samples for training the classification model. And also, we're gonna make here another training for the GAN using the same OGDB, but augmented with traditional data augmentation for rotation and flipping in X and Y. So, with all the new artificial data, we're gonna keep only the new images that are known to be as kind of original. I know they're artificial, but with an expert of biomedics here, he helped us to pick only the ones that seems like an original image of leukocytes. So then, we're gonna keep them together and have a new data set called master. With the data augmentation of GAN, we get now 1,000 images. It's more than 100% augmentation. And we're gonna use these two data sets to train the classification models. So now we're in the part of the leukocyte classification model. We make a compilation of various state-of-the-art works and carry out 3 models that were the best regarding the classification task based on the band metric. Band metric means balance accuracy value, and this one is better used for data sets that cause imbalance classes. So we ended up picking 3 models: AlexNet, BGG16, and ResNet 50. The 3 of them will be implemented with transfer learning, and the 3 of them trained with the ImageNet ImageNet dataset. But in AlexNet, AlexNet was presented in 2012. In 2012, we haven't that much of computational requirements. So the architecture that they present was working in a parallelism way. So they used 2 GPUs for training this model. Now we make a modification of this so it can be concatenated, these 2 pipelines, into just only one, so we can train it in 1 GPU. So we make this modification, but keep all the parameters as the ImageNet with transfer learning. So we're going to see some results. Well, we got 3 models. We need to select one of them for result classification task. So we propose 2 methodologies for picking the model: C variation and cross validation. With C variation, we will take the 3 models trained with both datasets, the OGDB and the master, changing the seed, the reads, every dataset. So we have a total of 12 experiments. And also, we will be making a cross-validation to validate that these 12 experiments are okay made and not seem towards a certain distribution of the images. So, we make 5 folds because we're training with 80% of samples for training and 20% for validation. And that will take us to 15 experiments. Here we can see the results from C variation, in which OGTV and master, we got the AlexNet as the best in both datasets regarding the ABAM metric, with a 98% classification and 92%. And in the cross-validation, also AlexNet gets a win with a 95% in average. So we like to think that AlexNet is the best classification model, and we select it for further analysis. So the data from the GDEM GAN. Well, as I said before, we use a data augmentation method with GAN and artificial samples. So here's our distribution in the master dataset, which has 52% of the samples generated from GAN and 42% from original images. So we say that we have a validation and training sets. Each of them have original and GAN images. So here comes the question, if really the GAN samples are helping generalize the model, or they are making that the model makes an overfitting towards the artificial samples. So we propose a new data set, Master Challenge, which in training, yeah, it has the GAN samples and some original, but in the validation, we only take original samples. So that way, we are really evaluating the model for a new set that may come in, well, in the field. So here we can see the results, the experiment of Master Challenge dataset, and the comparison with experiments of the cross-validation set, the full number 2 of the Master of AlexNet. And here we can see that we keep the performance of the model, so we can say that the model it is generalizing with the new GAN samples, and that we keep the same performance. Okay. Well, here we compare our model. The best one here was the one on C variation with the state-of-the-art models presented for local classification. We need to say that this is not like a direct comparison, because every one of these words was trained with a different dataset. But we can see only the comparison of the band metric. So we got the 4th place regarding all of the words stated out of the band. But the second one, considering that we use only one classification model for solving the test. So, well, considering the results above, we conclude that the simple AlexNet without extra components could solve efficiently the classification task with a performance of 98.17%. And that will vary like 0.6% from the first place. That is not much. Also, as I said before, that we got the second best performance regarding one hit model regarding the solve of the task of classification. But we need to say that the first place, according to the authors, they had to train 3 new layers, which may increase the training time. And they also reported that the prediction time presented a higher execution time, which is not suitable for a model that is intended to be implemented on an embedded system. So, well, we use only one model, so it can be better to implement on an embedded system because it doesn't require more components and it has a lower computational capacity. And we also demonstrate that our method with GAN is a good method, well, considering various things, but can be considered a good method for data augmentation. And in addition, we present a different data set with leukocytes segmented directly from images from the microscope. And as future work, we would like to implement the model in an embedded system, and so we train it using TensorFlow. So we're going to use ONNX to implement it on an NVIDIA Jetson Nano. And then after that, that model will be considered like a baseline model. So we like to make an optimization of the AlexNet model using a reduced neural architecture search considering a search page of the architecture Alex Nelvicio. So we can find a new version of the model Alex Nelvicio that requires less computational requirements and has the same or better performance as the base one. And with that new reduced model, we like to implement it on the Jetson Nano again and compare it to the base one. And here are some references, and that will be all for me. Thank you.
Thank you again, Fernando. And is there any question? I have one about this. Oh, okay. We have one question.
Thanks. Where is your interest to study white blood cells instead of another type of cells like, as you say, red blood cells or platelets? Why is the interest to study white blood cells? It's more complicated in hematologies, classificating leukocytes over in hemogram, for example, the segmentation of erythrocyte of hemoglobin or the red counting blood cells over the white blood counting cells. So why is the interest to study leukocytes?
Thank you for your question. Well, the purpose of this is because leukogram is one of the most common tests of blood. When we go to a doctor, they always tell us to make well, not a hemogram, but a hemogram, sorry. And a hemogram consists of the count of the three types of cells: platelets, erythrocytes, and leukocytes. But with leukocytes, we can define how a person can be like have an infection or certain type of disease. There are different considerations regarding the percent of each type of cell, and with that, the doctor can start and make a diagnosis of the patient's disease, so they don't be kind of lose where it's stuck. And also, well, this is actually made automatically right now in laboratories. But those equipment are very expensive, and they need a little bit, well, not a little, a lot of maintenance. So that keeps the cost high. So this will be cheaper, and will solve the tax as well.
Another question?
Thank you for your presentation. I have a question. In fact, in your did you consider use the model that was trained, or maybe it's necessary to retrain using an image maybe normalized, like in the previous paper, for example, using the difference in microscope, or maybe change the contrast?
Thank you. Well, we need to start at a certain point, right? We can't make research and have it all at the first time. So this is like a starting point with the classification part. But actually, something that I didn't say here, I'm only working with 100x magnification. So this will be better, and then in another stage to classify it with 40x classification images, because well, 100x needs a little bit more preparation with the microscope. We need to put an oil drop in the lens so it can focus better. And with a 40x, you don't need to do that, so it's faster the process. So this is here more like a start point. It will be good to make, well, to add new images from different microscopes, as you said, because they can vary with the light or with the lens a little bit, so it could be better for the model to better generalization.
Another question? Okay, if not, thank you again. You have your second debate of participation. Thank you. very much.
Thank you.
Then this last talk, we finish this session number 6. And thank you to all of you for your attendance. Yes, we have information.
Hola. Unos anuncios. Para la cena de la noche, la cena va a ser a las 7 allá en el hotel y es en un salón que se llama Los Principales. Está entrando en el primer